This one is C4H11ON, and that would indicate that we have 0 double bond equivalents. Now we can look at what we can see here. I can see two CH2 groups, so that's going to be two CH2s, and we've got a 6H here with a single peak. When we're deciding whether the 6H is going to be two CH3s or three CH2s, we can usually figure it out by the number of peaks. So when you've got 1, 2 or 3 peaks under the 6H, we're generally talking about two CH3s, and this is due to symmetry requirements. It's only when there's 4 peaks that we think about 3 CH2s for the 6H. And if you want to read more about this, you can stop the video and read this section of my guide. So the two 6H's here, that's going to be two CH3s. And then we've got a 1H over here. Now looking at the pieces we have left over, we have 1H, 1O and 1N. So that means we've either got an NH and an O, or an OH and an N. Now because we have this two CH3 groups here and it's a single peak, they're probably connected to the same thing. Now I know they're not connected to a carbon that doesn't have hydrogens on it because we don't have that piece here available. So the only thing I can really think of that the two CH3s might be next to that doesn't have a hydrogen on it might be a nitrogen. There's one other clue that I can look at here, and that's with the CH2 group, and that's at 4 ppm, indicating that's directly connected to an oxygen. Now there's nothing else in that region, so there can't be two carbons connected to the oxygen, which again leads me to be thinking that this 1H might be an OH and that the OH is connected to the CH2. So let's see how that will go. Obviously if it doesn't work, you can always reset the pieces and try it again, but there are good reasons for why I'm choosing the groups that I'm going to choose right here. So we're going to choose an OH, and we're going to choose a nitrogen that doesn't have any hydrogens on it. So that should be the correct pieces, and it is. And we'll go down here and begin to put the pieces together. So first of all, we know the two CH3 groups have no hydrogens adjacent to them, but they're related by symmetry. So the only way I can really set this up is to put this two CH3 groups here, connect them to the nitrogen like this, and then everything else is going to go in the structure. So the CH2 will go down here, this CH2 will go next to it, and the OH will go over here. Now the two CH2 groups, we know that they're next to each other because the CH2 groups themselves have 3 peaks. So this CH2 has 3 peaks, indicating it's next to 2 hydrogens, or a CH2. And this one has 3 peaks, so it's next to 2 hydrogens, or a CH2. We also know that the CH3 is not adjacent to the CH2, obviously for the reason that the CH3 is still a single peak here. So there is good evidence for having this kind of arrangement for our structure. The one other thing I want to point out is the OH here, and the fact that the CH2 doesn't couple to the OH. Now one thing we notice in NMR is that the multiplicities, or the splitting of the peaks that we see here, is always due to carbons on hydrogen atoms. So when you've got a situation like this, yes, the CH2 will couple to the CH3, but the CH2 will not couple to the OH. Likewise, the OH doesn't couple to the CH2. That's why this is going to turn out to be a single peak, and why the CH2 only appears as 4 peaks, because it's coupling to the CH3. And we're going to see the same thing with this structure as well.